Hi, welcome back from the break. Now we are going to look at the 2's complement, which is the equivalent method for the 10's complement, but for the binary case. We are going to apply mostly the same method to binary numbers, just like we did in the decimal case. For example, we want to calculate this. 10110 in base 2 minus 111 in base 2. We want to solve this question, but without using the regular subtraction algorithm. First, we confine ourselves to the world of 5 bits. Why 5 bits? Because the larger number has 5 bits. We could, for example, choose maybe 6 bits, 7, or even 8 bits, or any large amount of bits we want. But the choice of 4 bits or 3 bits would be a wrong choice here, because the large numbers won't fit in. We want both of the numbers to fit into our choice. So 5 bits is the minimal choice that you can do that is going to work here. We are going to begin by finding the 2's complement of the second number of 111. We are going to do it by calculating 1 minus b for every bit b. Some people also call this flip every bit. Flip means turning 1 into 0 or 0 into 1. Finally, we are going to add 1, just like in the decimal case. This is how it looks like. First, we take the number 111 in base 2. We extend it because we are going to work in the world of 5 bits. So we extend it with 2 0 bits. Now we do the bit flipping. We change every 0 into 1 and vice versa, and we get this number. And then we add 1. Finally, we get this result, 11001 in base 2. Now we can just add this number to the first number. We copy it here, this number 10110, and we copy this result, the 2's complement, 11001, and we add those two numbers. We add them in the regular way with the plus operator, and we get this result. As usual, we are going to consider only the lowest 5 digits, because we decided to work in the world of 5 binary digits. This is going to be our result. We get that 10110 minus 111 in base 2 equals this number, 1111 in base 2. We had this leading 0 here, and we can just remove it and stay with this result. We can actually check that this result is correct by using the calculator as usual. We pick the binary, and then we calculate 10110 minus 111 equals exactly this result. So we were correct. Some observations regarding the 2's complement. Using the 2's complement imposes a limit on the amount of bits used. That means we have to fix the amount of bits used before finding the 2's complement of a number. For example, let's look at this number, 101 in base 2. It will turn into 011 in the world of 3 bits if we invoke the 2's complement operation. However, it will turn into this number, 111011, in the world of 6 bits. So, it does matter. We have to make our choice in the beginning. Another interesting observation, adding a number with its complement gives 0. For example, if we take this number, 101, and add it with its complement in the world of 6 bits, we are going to get this result. As we consider only the lowest 6 digits, the lowest 6 bits, then we actually get 0. This should not be a surprise to you, mostly because the complement of a number should represent somehow its negative counterpart. This number is actually the minus of this one. in the world of 6 binary digits. Signed binary numbers. Let us look at all the binary numbers with 8 bits. This is also called a byte. We are going to discuss this notion a bit later in more detail, but it might be a good time to just be familiar with the name byte. We call numbers that begin with the bit 1 negative. We have to be careful about this because sometimes it could be hard to see which bit is the first one. And I will try to explain. When I say numbers that begin with the bit 1, I mean bit number 8. Usually it is going to be the first bit from the left, but you might encounter numbers which just have less bits. Maybe, for example, the number 110. The number 110 only have 3 digits, but you might think that it is negative because the leftmost digit is 1. However, if you extended to have 8 bits, then you could easily see that the first bit is actually 0. Thus, the number 110 in the world of 8 bits is actually positive and not negative. That is just an example. To change the sign of a number, we use the 2's complement method. For example, this number 10110001 in base 2 is a negative number. It is a negative number because of this digit, the 8th digit when we count from the right is 1. That means that this number is negative. The 2's complement operation is going to look like this. We take this number, we flip every bit first, and then we add 1. Just to make sure that we understand what's going on, make sure that you see that every bit is flipped. For example, the first bit 1 is turning into 0. The next bit 0 turns into 1, and so on. You can see also that the last bit 1 is turning into 0. Then we add 1 and we get this number, which is just 79 in base 10. That means that this binary number represents minus 79 in base 10, if we take into account the 2's complement interpretation. We call this representation of numbers the signed binary numbers of size 8, as opposed to the simple representation that we learned earlier, that is called unsigned binary numbers of size 8. What does this notion mean? What does signed mean? It means that it has a sign. It has a sign of plus or minus, kind of a virtual sign. The sign here is denoted by the first bit, but mostly in a virtual way. It's not really a sign. It's just the first bit that indicates the sign of a number. In the unsigned case, we just don't have signs because all the numbers are positive, just like we learned before when we didn't search for a solution for the signed number. We can add signed numbers in the usual way, and the sign of the numbers is taken into account automatically. This is something very interesting. The 2's complement is built in a way that the plus operator can actually understand it in some way. That means that if you add even a negative number with a positive number, you are going to get the right result. This is pretty amazing, and we are going to see more about it in the future.